केवल स्क्रीन शेयर कर
Yes.
मेरे
Okay.
प्रॉब्लम. Yeah. So starting केवल introduction वाली slide devices. Next one. Next one. Yeah. Previous one. Previous. पीछे जा. Terrestrial वाली पीछे जा. Yeah. Next slide. बस. So yeah, starting from the terrace, resuming the last time I stopped, introducing the scanner, a terrestrial scanner. It's a laser scanning device which locates objects at a distance, whether it's visible or not, and gathering data as three-dimensional points in space. The collected points are registered with each other using a reference station point, which can have geodetic coordinates like a northing, easting, or elevation, or local coordinates such as X, Y, Z. Now, the data obtained from laser scanning is presented as a point cloud comprising tens of thousands of or more points captured by a laser scanner, which then is processed under some software for editing or exporting the data into different formats. Moving on to next device, which is drone survey. It's basically a drone conducting an survey and with sensors like RGB or multispectral cameras and LiDAR to capture the aerial data. In the case of an RGB camera, the ground is photographed from various angles and each image is tagged with coordinates. Then the data is processed using photogrammetry software to generate georeference or orthomosaics. These maps then these orthomosaics or these tiles then convert into maps. These maps then were extract detailed information such as highly accurate distances or volumetric measurements, providing valuable insights for various applications. Next slide. The next device would be SLAM scanner. It's a technique used in robotics and surveying to create an environment map while simultaneously tracking the position of the sensor with that environment. In this device, it usually creates a AR kind of thing. Like you can imagine the whole environment using this device after the scanning. And then it suggests using a scanning device that employs SLAM technology to map an area in real time while determining its location within that space. The survey would involve moving the scanner through the environment, allowing it to build a map and understand its position related to the surroundings. The next one is total station. It's a simple but yet powerful device which gives the combination of angle and distance measurements through the combination of theodolite, which measures angles, and a distance meter that uses laser for or infrared technology for measuring the distances. The seamless integration of these functions makes the total station an essential tool in fields such as construction and civil engineering. Now, the next and the last device would be DGPS survey. The DGPS is used to refine the accuracy of GPS-based location data by comparing the calculated position from GPS signals with the known position of a stationary reference station. DGPS introduces correction factors to mitigate errors caused by atmospheric conditions and satellite clock inaccuracies. This process significantly improves the accuracy of location data, making DGPS surveys valuable in applications such as land surveying, precision agriculture, and marine navigation, where precise positioning is essential for reliable results. Next slide, Kevin.
So now comes data processing. Once we have gathered all the data, raw data for the surveys, we will come to its processing. The processing for terrestrial scanner involves processing the point clouds that it generates. since terrestrial scanner is mounted on a tripod, we have to move it from place to place and take different scans. These point clouds needs to be stitched together with minimum 30% overlap to give a scalable mesh. The software used here will be a FarrowScan, and this software slide, okay. This software will be used for SLAM scanner also. Since SLAM scanner is a continuous process, we won't have to stitch point clouds, as the SLAM scanner would form a continuous loop over the area surveyed. The final output generated here will also be a scalable mesh. Drone survey. As Shripad explained, a drone captures RGB photos from a height. So these photos also need minimum 80% overlap to form a correct output. And these photos will be stitched together first, then they will be aerotriangulated, and then we have used a technique called ground control points to increase the accuracy of these surveys. So we will take 3 photos of a single point, which will have X, Y, and Z data of the ground. These will be inputted in the actual images that the drone has taken, and it will autocorrect its location in all the 3 axes to form a correct output. The final output generated from drone survey will be a 2.5D model and 3D model. 2.5D model is a digital elevation model that can be imported in Google Earth and has data regarding the Z axis of a plane. The DGPS survey and the total station survey were used as ancillary surveys to improve the quality of the other advanced surveys. As you can see in the images below, the black and white square like paper that we have mounted on the wall is checkerboard, and the yellow marking that we have done on the ground is ground control point. The elevation for these points will be taken from total station, since the accuracy of total station and DGPS survey are very high. This will be inputted in the drone survey, SLAM scanner survey, and terrestrial scanner survey to increase its accuracy, as discussed before. Output generation. So these are the images of the outputs that we have generated. The image on the top right is of the terrestrial and SLAM scanner model. This is a 3D model, and .3sm file means scalable mesh. You can move around, and you can even measure distance, area, and other things. The 2.5D model, as you can see on the image below, we have imported it on Google Earth, and it has been overlaid on the actual location, and it has been exactly overlaid. So this again verifies our accuracy. The image on the bottom right is of the SLAM scanner survey. Even the brick lines are visible, so it can be used to detect cracks and other things. So its use will be the contractors, engineers, and other workmen that won't have to go to the site for continuous evaluation of the site. It will save time. The images on the left are 3D models of drone. Please.
So you are left
from
with
different
1 minute.
angles. Yes, thank you. So there are 2 types of outputs generated: 2.5D model and 3D model. Okay, data validation. Shripad will take on from here.
Yeah. So data validation. The left one was we have validated a drone's service 2.5D model overlaid on the Google Earth, and we have done RAMSE calculations for DGPS and terrestrial output for elevation, and compared with each other, like taking DGPS coordinates and terrestrial data coordinates and comparing with and calculating the area and all that, how much it is accurate and all that. Next slide, Kevin. So yeah, the conclusion for this whole research paper was drone surveys excel in capturing areas inaccessible to terrestrial and SLAM scanners due to dense vegetations. 3D modeling software like AutoCAD or QGIS enables additional data extraction or aiding in slope analysis, area volume calculation, and point cloud point location determination. Drone enhances safety, efficiency, and ecological impact across industries like land surveying, logistic, construction, and site management. Coming to terrestrial laser scanning, it's combined with photogrammetry, enables precise data acquisition and 3D modeling. SLAM scanner can be used in heritage management, utilizing LiDAR and LiDARs and sensors for accurate site modeling, accessing in accessible areas with lightweight equipment. Terrestrial laser scanning in architecture, engineering, and construction facilitates rapid data collection and measurement despite equipment limitations. Overall, this technology revolutionize cultural heritage preservation and technical inspections with efficiency and accuracy. Excellent. Thank you. Any questions?
Thank you for your presentation, sir. If anyone has any question from this presentation, then they may ask.
I have a question actually. Since you mentioned QGIS, would it be possible to use satellite data for constructing models, though that would be less accurate, but wouldn't it still be possible to use satellite data for constructing digital elevation models?
Yeah.
Triple?
Yeah, ma'am, you take the question.
Yes. So what you said that the satellite data we can use, but mainly we are targeting for this particular technology for the construction practice. In construction practice, we are dealing with almost level of the accuracy. So satellite data is used only for the planning purpose, not for the implementation purpose or the construction purpose. That's why we are not using. But as what we are going to do, we are just trying to see that how this technology can be that inferences along with the satellite data. So what we have done over here, we have utilized total station and DGPS survey to just enhance the output of the terrestrial scanner as well as this LAM scanner or a drone technology. Standalone technology, they are generally giving a centimeter level of accuracy. So I think with satellite data, we cannot achieve this kind of the accuracy. That is one of the limitations, but planning stage, we can use this remote sensing or the satellite data for the same.
Thank you.
Yeah, thank you.
Okay, any other queries from anyone? Okay, I would request you all to please keep the time limit in your mind, that is of 6 minutes. Okay, now I would like to call Athar Digambar for his paper presentation on the paper title, Data Compression for Backbone Network.
Yes, ma'am. Can I share my screen?
Yes, sir.